Hello, welcome to Chapter 1.2 Part 2. And in this part we're going to discuss about the binary system. The binary or base 2 system is written only with ones and zeros. Binary is the language of electricity since an electrical impulse is either on, which is 1, or off, 0. Binary is the deepest language inside the computer. The number 1101 base 2 is on, off, on. So 1 represents on, 1 represents on, 0 represents off, 1 represents on, and of course the little 2 here is base 2. So the only numbers represented in the base 2 system are zeros and ones. Any other number, that means it would not be in base 2. In example number 1, we are asked to convert 1011101 base 2 into base 10. So let us go over to the whiteboard and work this out.
In this example, we have 1, 0, 1, 1, 1, 0, 1, base 2. In base 2, the 2 tells me that it's binary, but in the binary system, we only have zeros and ones. If there is any other number other than a 0 or a 1, then it is not binary. So remember, in the binary system, there are only zeros and ones. So what we do is we set this up the way we have before in a table. And I have the 1 from there. And I have a 0 from here. And then I have my 3 ones, 1, 1, 1. And then I have another 0. And then I finally have a 1. And this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3rd, 2 to the 4th, 2 to the 5th, and finally 2 to the 6th power. And 2 to the 6th power, well, we calculate that and we find that's 64, so that's the 64's column. 2 to the 5th power is 32, so that's the 32 column. 2 to the 4th is 16, so that's the 16's column. 2 to the 3rd is 8, that's the 8's column. 2 squared is 4, so that's the 4's column. 2 to the 1 is 2, and of course anything to the 0 power is 1. So now we multiply 1 times 64 plus 0 times 32 plus 1 times 16 plus 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1. So here we get 64 plus 0 plus 16 plus 8 plus 4 plus 0 plus 1. And we add all of that up and we get 93. So all of this, these zeros and ones, what it means is 93 in our base system, which is base 10.
Now let's review what we just did on the whiteboard. So we make a place value system for the powers of the different bases. In this case, it's base 2. So here's our table. So we go all the way up to this 1 here. So we start here. The 1's 2 to the 0. The next place is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and then finally 2 to the 6 represented here. Then we write in our number. So we have 1, 0, 1, 1, 1, 0, 1. And then we do our multiplication, because this is the 64 column. 1 times that. This is the 32s. There are no 30s, so that's 0. 16s, 1 times 16. 8s, 1 times 8s. 4s, 1 times 4. 0 times 2, 1 times 1, and then, which is what we just did, we multiply the digits of each place value, and then finally we add them up. 64 plus 0 plus 16 plus 8 plus 4 plus 0 plus 1, and we get 93. In example number 2, we're asked to convert 10, 10, 10 base 2 into base 10. So here again, we're going to work this out on the whiteboard.
In this example, we have 1, 0, 1, 0, and 1, 0. And it's base 2, which means that it's binary, and you can tell that it's binary because there's only zeros and ones here, but they're counted not like 10,000 or 101,000 or anything like that. They're just called 10, 10, 10. So we want to convert that into our base 10, which is our base. So as before, we'll construct a table. Because we're going from the binary. So we'll put a 0 here. I'll put a 1 here. And I'll put a 0 here. And a 1 here. And I'll put a 0 here. And one more 1. And now I'll figure out how far I go. So 2 to the 0. I always start out to the 0 power. 2 to the 1. 2 to the 2. 2 to the 3rd power. 2 to the 4th power. And this I only have to go to 2 to the 5th power. So 2 to the 5th power we found before was 32. 2 to the 4th power is 16. 2 to the 3rd power is 8. So that's the 32s, 16's the 8, 4, 2, 1. And so this is 1 times 32 plus 0 times 16 plus 1 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. And so that's 32. And plus 0 plus 8 plus 0 plus 2 plus 0. And we add it all up and we get 42 in our base, which is base 10.
Reviewing what we just did on the whiteboard, we make a place value table for powers of the different base, in this case base 2. So here we make our base 2 table, and then we fill in seeing how many places there are. So we have the 0, 1, 0, 1, 0, 1. So that means we go from 2 to the 0 to 2 to the 5th. And then we multiply the digits by each place value and add. And in this case, it's 32 plus 0 plus 8 plus 0 plus 2. And when we add all those up, we get 42. Now we're going to convert 42 back into the binary base 2 and see if we get back the same number that we got in example number 1 for the base 2 binary number. Let us go over to the whiteboard and work this out.
In example number 3, we're going to take 42 in our base system, which is base 10, and we're going to convert it into binary, which means ones and zeros. So to make our binary table, we want to figure out how far we have to go. Well, if we go out to 2 to the 6th, we find that 2 to the 6th is 64. And we see, well, that's too high. So let's go down to 2 to the 5th, and that's 32. So that's as far as we really have to go, because 32 can go into 42, but 64 is just too big. So we construct our table. 0, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and our last 2 to the 5th. And we know this is our 32s, this is our 16s, this is our 8s, this is our 4, 2, 1. So now we want to see how many 32s go into 42 and what the remainder is. Well, we see that 32 goes into 42 once, and the remainder is 10, because 42 minus 32 is 10, so remainder 10. So then we bring the 10 over here. So we see that 10 divided by 16, well, that doesn't go in, so we have still a remainder 10. Then we go to the next one. 10 goes into 8, and we see that goes in once with a remainder of 2. So now we take the 2, and 2 divided by 4, and we see that is 0. So we just have to carry over the remainder of 2. Then we have 2, and we see that 2 divided by 2 is equal to 1. So that means we have a 1, and there's no remainder, so that means this last one is 0. So now we can write the whole numbers here. So we have 1, 0, 1, 0, 1, 0 in binary. That's why it's a subscript there. That's telling us it's binary, and that's what we would hope that it would be.
Now, in reviewing what we just did on the whiteboard, we made a base 2 table up to the highest number 42 divides into without going over, which is 32. This is how we know how the highest number to go up to, because 2 to the 6th is 64, and we know that's too high. So we make our table, and we subtract to get the remainder. So 32 goes into 42 once with a remainder of 10, or 10 left over. And we also can write 42 divided by 32 is equal to 1.3125. And that's the same thing, because if you're using your calculator, you'll get that. All you want is the 1, and so you have 42 minus 32 will give you the remainder. And we construct the following table, as we did on the whiteboard, with all the remainders. So for the first one, 42 over 32, we get 1 with a remainder of 10. We take the 10, we have 10 divided by 16. Since 10 can't divide by 16 as any whole number, we still have a remainder 10, and then we take the 10 divided by 8, and we get 1, and there we have the remainder 2, and so on. And we add these up, 32 plus 0 plus 8 plus 0 plus 2, and we get 42. So the answer is that 42 in our base system is equal to 101010 in base 2, or in the binary system. That's what the little 2 means. And this would be what we would expect, because that's what we saw in the other direction. Thank you very much. I hope you enjoyed this video, and I hope that it helped you understand a little bit more about the binary system. So take care, be well, bye.